Welcome back to Science Click. Today, the mathematics of general relativity, part 5, curvature. Our mathematical model is almost complete. Using the metric tensor, which allows us to measure distances in space-time, we know how to predict the movement of objects by introducing coordinates, velocity, and the geodesic equation. But the great power of our model is that it makes no assumptions about the geometry of space-time. In the previous videos, our sheet of paper was always represented as a flat plane. But nothing prevents us from imagining a curved paper on which we can just as easily define coordinates and thus describe the movement of objects. Space-time is not always flat, its geometry can be bent, and its curvature will have interesting effects on the trajectories of bodies. If space-time is curved like a sphere, for example, two parallel geodesics starting from the equator will get closer to each other. It is this kind of phenomenon that we use to model gravity. The curvature of a surface is a key concept in general relativity, and will need a rigorous definition in order to use it. Imagine a plane with a square grid and a sphere with coordinates of latitude and longitude. Let's place an identical vector on these two surfaces. On both surfaces, we will transport the vector up and then right. This gives a new image of the vector, which has been transported along the surface. Now let's transport the same vector to the same point, but moving it first to the right and then upwards. On the plane, these two images we get are the same. Whether we transport the vector right or up first does not influence the final image of the vector. On the other hand, on the sphere, the two images are distinct. They are oriented differently. This effect is what we call curvature. Some surfaces are flat. The image of the vector does not depend on how we transport it. And inversely, some surfaces are curved. The path that the vector follows influences its final orientation. Now that we have a definition for the concept of curvature, we can express it mathematically. On our surface, let's choose a basis vector. Then, we choose two coordinates to transport the vector. We can choose the same coordinate twice, or more interestingly, two different coordinates. We denote them mu and nu. Now transport the vector, first along mu, then nu, and secondly along nu, then mu. We thus obtain two images of the initial vector. Performing the difference between these two images, we get a new vector, capital R. If the surface is flat without curvature, R is 0. And the more the surface is curved, the longer this difference vector becomes. The vector r is the difference between two derivatives of the basis vector in opposite orders. Indeed, we transported the basis vector first along the coordinate mu, then nu, and then along the coordinates nu, then mu. We saw previously that derivatives of basis vectors give us Christoffel symbols. After a few replacements, we get a final expression for this vector r that we can break down into its components. The set of all these components, these 16 numbers that describe each possibility for transporting basis vectors along the surface, is called the Riemann curvature tensor. It fully describes the curvature of a surface. As soon as we know the metric tensor, we can calculate the Christoffel symbols and hence determine each component of this curvature tensor. The Riemann tensor encodes the curvature of a surface in all possible directions. It is a complete tool for describing geometry. Unfortunately, its 16 components make it a very heavy object to handle. Some of these components repeat themselves, and others are always zero. Even worse, in the case of a true four-dimensional spacetime, the curvature tensor has 256 components. To simplify, we need to derive two efficient tools that describe curvature but are more convenient for calculations. The first of these two objects is called the Ricci tensor. The Ricci tensor is represented as a table, with one row and one column for each coordinate. To determine a component of the Ricci tensor, for example its 0, 1 component, we start from our curvature tensor. Among all its components, we select those whose second and fourth indices are the indices that we want to calculate. In this case, 0 and 1. Among the remaining components, we keep those whose first and third indices are the same. Finally, we sum the remaining components. Intuitively, the Ricci tensor measures how volumes change on the surface when we move along its curvature. On a sphere, for example, the volume between two parallel geodesics decreases as we progress on the surface. The components of the Ricci tensor measure these variations of volumes along the different directions of the surface. But for certain symmetric surfaces, like a sphere, the curvature is the same in all directions, and we can therefore describe it by a single number. This number characterizes the average curvature in all directions, and we call it the Ricci scalar. In the case where our coordinate system is orthogonal, with axes perpendicular to each other, the Ricci scalar is easy to calculate. It is the sum of each component on the diagonal of the Ricci tensor divided by the same component from the metric tensor. Finally, let's illustrate this concept of curvature with two concrete examples. The first example is that of an empty spacetime, with coordinates t for time on our clock, and x for space along an axis. We saw that this spacetime is described by the Minkowski metric, which takes the following form. The components of the metric tensor in this empty spacetime do not depend on the coordinates, they are the same everywhere on the grid. Consequently, their derivatives are 0, which implies that the Christoffel symbols are all equal to 0. Therefore, the Riemann and Ricci tensors and the Ricci scalar all vanish. The Minkowski spacetime is flat, it has no curvature, and two objects starting parallel to each other will never meet. The second example is that of a sphere. At a point on the sphere, described by its latitude and longitude, the metric tensor takes the following form. This time, the metric tensor is not the same everywhere on the sphere. It depends in particular on the latitude coordinate. By calculating its derivatives, we can obtain the expressions of the Christoffel symbols. And from the Christoffel symbols, we can calculate the various components of the Riemann tensor, the Ricci tensor, and finally the Ricci scalar. On the surface of a sphere, the curvature is positive, which means that two parallel geodesics tend to approach each other. Furthermore, the curvature gets smaller as the radius of the sphere increases. The larger the sphere, the flatter its surface.